Hello everyone, my name is Jian Xiang. I'm a postdoc at Harvard University. Today I'm going to present called Inflow, a coarse-grained information flow control for Java-like languages. This is joint work with my supervisor, Professor Stephen Chong. The broad motivation for this work is to investigate how to add information flow control mechanisms to existing programs. Many existing programs handle sensitive information. IFC mechanisms track the flow of sensitive data through a system and stop programs from violating security policies. A lot of effort has been put to IFC mechanisms. These mechanisms may be static or dynamic. Static mechanisms are often called secure type systems, which use type checking to ensure no information leak of high security content to low security channels. The benefits of static mechanisms include reduced runtime overhead and fewer runtime failures. On the contrary, dynamic mechanisms track how information propagate and enforce security policies at runtime. Dynamic mechanisms are often more flexible in dealing with runtime data and policy change. From another point of view, IFC mechanisms can be categorized as fine-grained or coarse-grained. Fine-grained mechanisms associate security labels with variables and values, while coarse-grained mechanisms often associate labels with computational containers. For example, a lexically or dynamically scoped section of code. Compared with fine-grained mechanisms, coarse-grained mechanisms are often less intrusive. They require less changes to existing programs and pose relatively smaller runtime overhead, since fewer entities are tracked. We believe that coarse-grained dynamic IFC is a good match for an imperative OO programming language such as Java. Our CoreInflow tool makes it easy to add IFC to existing Java programs with good precision, low user effort, and low overhead. It does this by aligning coarse-grained IFC concepts with existing Java abstractions. Method calls are natural computational containers, objects are natural data containers. As such, Java can be cleanly extended with coarse-grained dynamic IFC without requiring significantly different design patterns or extensive security annotations and without extensive performance overhead. Let's briefly go over a few concepts in CoreInflow. We will present some examples later. First, we talk about computational containers and context table. Coarse-grained IFC is based on the idea of computational containers, which are contexts where computation happens. In CoreInflow, every method invocation creates a new computational container, so every stack frame is a container. A method call will add a container on top of the current stack of containers, and the container is destroyed when a method call returns. Every computational container has a context label. It is the secure label that is an upper bound on all information that has flowed into the container. Context label is also called floating label, a current label, or program counter in related work. As more information enters the container, the context label is increased in order to remain an upper bound. The third concept is field label, designed for objects. Every object has a field label that is an upper bound of the information stored in its field. If an object's field label is L, when data is read from a field of the object, it is treated as information with label L. Field labels of objects do not automatically float upwards. In CoreInflow, programmers can use a special operator to read the field label of an object under a certain security condition. The fourth concept is labeled values. A labeled value is a pair of a value V and a security label L that is an upper bound on the information on which V depends. Labeled values are used often in dynamic IFC mechanisms such as IOIO. Intuitively, a labeled value can be passed around by a container without the container's context label being raised, so long as the container does not examine or compute on the value V. A container can unlabel a labeled value which raises the context table to at least L and allows the container to compute with the value V. Another key concept is opaque labeled values. Opaque labeled values are special labeled values which CoreInflow implicitly, automatically, and securely insert into programs to relieve programmers from their annotation burden. Now, let's see how some of these concepts work with an example. Please note that we mainly use this example to show how computational container and context label work. This example doesn't demonstrate how call inflow works. We will get to it later. This call snippet on the left is the main method that retrieves, formats, and updates Alice and Bob's phone numbers. A class named person is used here. It has a field called phone number and the getter set methods for the field. A static method format number is used to format Alice and Bob's phone numbers. As shown on the right, the execution of the program starts with a computational container for the main method. Two objects, Alice and Bob, are used in this example. Assume that initially the context label of the main container is button, which is the most permissive security label. The field label of object Alice is LAlice, and the field label of object Bob is LBob. The method called Alice get phone number creates a new computational container, and its initial context label is also button, the same as the caller. Now we are inside the callee's container. The left side of the screen shows the definition of class person, including the body of get phone number. The method accesses the field of object Alice. Reading a field of object Alice means information with label LAlice flows into the container. The context label increases to LAlice to maintain an upper bound. Then the callee container finishes execution and returns to the caller. After the callee finishes, its return value flows back to the caller. Then its context label increases from button to LAlice to maintain an upper bound. Then the method format number is called, which creates a new computational container. Its initial context label is LAlice, the same as the caller, since information flows from the caller to the callee. Inside the callee container, no new information is read. Its context label stays at LAlice when it returns. Return to the caller side. The callee returns with context label of LAlice. The caller's context label is already an upper bound. Continue execution. Alice set phone number is called to update the phone number. It creates a new container with context label LAlice. Inside the callee container, the method call tries to store the newly formatted phone number into a field of object Alice. When data is stored into a field, the object's field label must be an upper bound of the context label. Here, the field label of object Alice is LAlice. The context label is also LAlice. The field write succeeds and the method call returns. Return to the caller side. No new information flows in, so the caller's context label stays the same after the call. Now we format Bob's phone number. Similar to Alice get phone number, the method called Bob get phone number accesses data with label LBob. So the context label of the callee is the join of LAlice and LBob when it returns. When the callee returns, the caller's context label increases to the join of LAlice and LBob to maintain an upper bound. The method format number is called again to format Bob's phone number. The callee doesn't read new information, so it returns with context label of the join of LAlice and LBob. The caller's context label is already an upper bound. Next, the call Bob's sent phone number is invoked to update Bob's phone number. Inside the callee container, the method call tries to update a field of object Bob. Remember that the field label of an object does not float upwards, so because the context label, the join of LAlice and LBob, does not flow to LBob, the field write failed to indicate a possible security violation, and the program hunts. This example demonstrates how computational container and the context label work. Context labels can soundly track and control the flow of information. However, in some cases, it is imprecise. That is what happened here. The data written to the field of object Bob depends only on information with label LBob, but the context label was the join of LAlice and LBob before updating Bob's phone number. The program unnecessarily hunts due to such imprecise tracking. The precision of coarse-grained information flow tracking can be improved through the use of labeled values. As mentioned, a labeled value is a pair of value and a security label. In core inflow, the class label implements labeled values. Expression toLabel EL creates a new computational container to evaluate expression E and protects its result with label value L. allowing the programmer to control unnecessary increase of the context label, known as the label creep problem. The operator field label of retrieves the field label of the argument object. This example shows a modified version of the previous example by using labeled values. Let's see how it works. Here, we construct the labeled value using the toLabel operator for the method called getPhoneNumber and the field label of object Alice. The callee container accesses Alice's phone number, and its context label is LS when it returns. The toLabeled operator packs the return value into a labeled value and protects it with the label of LS. The context label of the caller doesn't need to be increased, since it has not read the information. Then we use toLabeled operator to run the method called formatNumber and send the labeled value to the callee. Inside the callee container, we access the labeled value with another primitive operator onLabel. It reads the value inside the labeled value and writes the context label to at least the label of the labeled value. In this case, Alice. The rest of the method body doesn't read new information until the method returns. Return to the caller side, the return value of a formatNumber is again packed into a labeled value, and the context label of the main container doesn't need to be increased, and stays at the bottom. The same situation applies for the subsequent calls. The context label of the main container remains bottom throughout the execution. Now, let's look again at what happens in the call Bob set phone number. A new container is created for the call, and the labeled value B1 is passed to the callee. Its label is LBob. Inside the callee, the input labeled value is opened by the onLabel operator. Context label increases to LBob, which is the label of the input label value. Then the field write check if context label flows to the field label of object Bob. This time it succeeds. The program continues execution. As shown by this example, labeled values enable more precise tracking and control of information flow. The use of labeled values can improve precision. However, there are issues. First, it requires significant program effort to add toLabel annotations. Second, it reduces readability. Third, it may require changing many method signatures to pass and return labeled values. To address these problems, the call inflow runtime essentially inserts toLabeled and onLabeled annotations automatically without burdening the programmers. Intuitively, call inflow's vision is that the programs look like the left, but they execute as the right one. So the program on the left is Java code, but when treated as call inflow programs, the implicit insertion of labeled values ensure that the runtime behavior is almost the same as the program on the right, but without the need for program annotations or changed signatures. The implicitly added labeled values are called opaque labeled values. There are differences between opaque labeled values and the labeled values. In particular, for every computational container, call inflow creates an opaque labeled value for its result. The opaque labeled values are then dynamically tracked in subsequent computation. Typically, in coarse-grained IFC languages such as IOIO, the program must supply a label to the toLabel operator. Call inflow removes this annotation burden by using the context label as the label for the opaque labeled values. The label of an opaque labeled values may itself reveal information. To prevent this convert channel, call inflow does not allow code to inspect labels of opaque labeled values, which is why we call them opaque. In addition to method calls, call inflow implicitly creates new computational containers for field reads. That is, each field read is executed in its own container, which helps prevent unnecessary increase of context label. We summarize the main results produced by this work. On the theory side, we model the essential parts of call inflow with a calculus and prove that it satisfies security property timing insensitive non-interference. The calculus and the non-interference proofs are mechanized in code. On the practical side, we implement the call inflow prototype, which supports most features of Java 8. To evaluate the feasibility and effectiveness of call inflow, we use the prototype to conduct several case studies, and the results indicate that call inflow is able to enforce information flow policies in existing Java applications with very few annotations and reasonable overhead. We also evaluate the position of call inflow with an information flow benchmark. The results shows that call inflow is as precise as other tools, and its precision can be improved with more annotations. One limitation of call inflow is that we cannot precisely track information flow caused by exceptions. We leave that to future work. To conclude, we introduce call inflow, a language that demonstrates coarse-grained dynamic IFC is a good match for imperative OO languages such as Java. That's all for the talk. Due to time limits of the presentation, we glossed over a lot of details. Please find more information in our paper, and we are happy to chat offline. Thank you very much.